Let's get some partial derivatives, shall we? First of all, we're going to find the second partial derivatives of this first function. Now, to get a second partial derivative, you do need to get a first partial derivative. There's no single step way to get all the way to number 2. So what we're going to do is start out by finding the derivative of this with respect to u. A note on variables, by the way. It's common to use variables like u and v and w the same way that x, y, and z get used. You should get comfortable with seeing like lots of different configurations of variables. U and v are common to use as parameters. So are s and t. And w, x, y, and z are common to use when you want like 2, 3, or 4 orthogonal different directions. But that's just for variables. For computation, it's going to be convenient to think of this as u squared plus v squared to the 1/2 for obvious reasons. Power rule, right? So partial derivative with respect to u would be, let's see, u squared plus v squared to the negative 1/2, that times positive 1/2, and that the derivative of the outside is what we've got so far, times 2u. These go away, and you end up getting u over the square root of u squared plus v squared. But really, it's going to be more convenient to write it as a product because we're going to eventually be taking another derivative. And I'd rather do product rule than quotient rule. So this is going to be u times u squared plus v squared to the negative 1/2. Now, partial derivative with respect to v, this whole thing is symmetrical because the u and the v could switch places and it would be the exact same function. So I can just immediately know that this will be v times u squared plus v squared to the negative 1/2. Again, symmetrical means that if u and v switched places, nothing would change. So I know that this is going to be definitely the same thing as the u derivative. It's just that now the v is in the place of the u. Okay? All right. So now I want to find the second partial derivatives. I'm going to take the derivative with respect to u and differentiate that with respect to u again. Woo! Get it? W-U-U? Yeah, no. So I'm going to take, I'm no longer referring to the original function. I'm referring to the derivatives now. So this will be the derivative of that with respect to u. It will be the product rule. Derivative of the first, which is simply 1, times the second. That's the easy part. And then plus the first times the derivative of the second, and this is going to be the hard part, the bad part. So this is going to be times negative 1/2 times u squared plus v squared to the negative 3/2. And so far, this is only the derivative of the outside, but I need the derivative of the inside as well. With respect to u, that's 2u. So the 2's go away. And the u's merge to make a u squared on the top. Now that this is no longer, I'm not going to need to do anything to this. I'm going to actually get it into a more convenient form, like 1 over square root of u squared plus v squared. And then this will be minus, there's that minus sign sneaking in there, minus, let's see, u squared over u squared plus v squared to the 3/2 power. Now I'll take WUV. Hopefully I'm going to have enough room to fit all of these. WUV. For this, I will once more refer to the u derivative. This is no longer symmetrical because the u is on the outside. So I can't treat this like I did with the original derivatives. But it is easy. It's actually very easy because the u being on the outside was what made it a product rule scenario before. Now it's not a product rule because u, from the perspective of v, is a constant. So actually this is a single function. So it's going to be u regarded as a constant from v's perspective, times negative 1/2 times u squared plus v squared to the negative 3/2. That's the derivative of the outside, and derivative of the inside from v's perspective is 2v. So these 2's vanish, and I end up with negative uv over u squared plus v squared to the 3/2 power. Let me get the next one. I'll get WVV. WVV is going to be that I now focus on this as the original. And I'm going to differentiate it one more time with respect to V. However, I already did this really when I did the WUU, because look at we can appeal to symmetry again. It's just with the V in the place where the U used to be. So I can say this is going to be 1 over square root of U squared plus V squared minus V squared over U squared plus V squared to the power of 3/2. Do you see how I formed a likeness to this? It's because in WU, U was in the same place that V is in WV. So there's a nice reversibility there. Only one more to go, WVU. Now, because we know that this is like a well-behaved function, it should do nice things, that we should get that WVU is the same as WUV. So we're expecting that we'll get this. If we didn't, it means we made a mistake. So WVU is you look at the V and differentiate it one more time with respect to U. And I could say I've done this already by talking about WU and then V. But actually, yeah, you know what? I will say exactly that, because it is true. Because the same thing happens here, that the U and the V have switched places. It used to be that WU was U on the outside, but now WV has the V on the outside, and everything else is reversible. So this is going to be negative UV over U squared plus V squared to the power of 3/2. And I'm not using Clairaut's theorem there. I'm saying that because it's symmetrical, because it's comparable in the sense that U and V have switched places, it's definitely equal to that. So notice, though, that that forces these to be the same. And we want that. That should be true in general, that mixed partials should be the same. Speaking of which, problem number 2 says that we should verify that the mixed partials are equal for this specific function. So we'll be finding, and now we're doing problem number 2 here. We're going to find partial U, partial X, with the aim of taking partial U, partial X, and then Y. So partial U, partial X is, let's see, y e to the y. That's a constant from this perspective, so it will be y e to the y. And then partial U, partial X, and then Y is the derivative of that with respect to Y. And this is product rule now. It's derivative of the first times the second plus derivative of the second times the first. Correct? You can take a second to think about it. Okay, agreed. Now we need uy with the goal of getting uy and then x. So uy is going to be x regarded as a constant now times the product rule applied to y e to the y. Well, we just got product rule of y e to the y. It's e to the y plus y e to the y. And then u partial y, then partial x is, and think about this, now x is multiplied by a certain number. E to the y plus y e to the y is a constant from the perspective of x. So this is now regarded as constant. So we can think of this as simply x times a given constant. And we already know what that's equal to. It's equal to the value of the constant, e to the y plus y times e to the y. And we've got equality of mixed partials. We've got that u xy is equal to u yx, just like we were hoping would be true.